Okay, so for those of you guys gone yesterday, I think this is probably the easiest way to see that we have to be careful on some polar curves because, ooh, see how the area would get double counted if I did 0 to 2 pi? However, is it enough just to stop right before the inner loop if I wanted everything, the entire area, not double counted? No, why? What if I stopped before the inner loop so I don't get that double counted, but what do I miss out on? So either I could choose here and go all the way and then double it, or I would have to do the entire thing and then subtract the inner loop, right? Interesting. Okay, let's go back. Nope, not to that. What do we do on this guy? Pause. Graph. Sketch. Figure out when the inner loop occurs, which might be graphing and sketching. It might be playing around with zeros. Zeros. St. Patty's Day is over. Oh, wait, that's leprechaun. Limacon made me think of leprechaun. Leprechaun made me think of St. Patrick's Day. St. Patrick's Day made me think of... It's done and over. I don't know. Guys, whoa, whoa, whoa. What are you thinking? What are you doing? We're working on this problem.
I'm graphing in my calculator.
No, that's the worst thing to do. But you can check. You can check later. You could start plugging in points to get a feel for how the limacon progresses. That's one way. Where are notes? Another way is you can maybe set equal to 0. Because the inner loop comes into a cusp and then repeat. So do what you think is easier. You guys agree? If you didn't graph, my question is, did you figure out at 2 pi over 3? And 4 pi over 3? Because that would be when cosine equals -1/2, which is going to be in the second and the third quadrants at the pi over 3's. Why is that helpful? Why is that important? Whether you figure it out here in that, ooh, there's that inner loop, or with the zeros. What am I supposed to be doing again? And the area formula for polar is 1/2. My bounds are going to be, or 2 pi over 3 doubled. Either way. The 2 pi over 3 to 4 pi over 3 would have us going out for this whole region. My R, wouldn't my R just be my outer or my function? It's not top or bottom or right or left, it's outer. So my outer would be the function, and the inner would be technically 0. And so we could just plug in our 2 cosine theta plus 1 squared. Since John and Jason are both gone yesterday, guys, what if we had to solve this by hand? You can't do u sub, because du would be sine. You can square it. You can FOIL it.
Cosine is equal to something.
I think you're thinking of 2 cosine squared of theta minus 1 being the double angle of cosine. Oh. You could make cosine squared into 1 minus sine squared, but that's not going to really help us much. Can we integrate 4 cosine? Yeah. 1? Yeah. This guy? No. I can change it with the power reducing formula for cosine squared. There was one I said way back in pre-cal would be helpful eventually, and now is the eventually. Cosine squared and sine squared are both super similar. Cosine squared says 1/2 of, right? Whereas sine says 1 minus. Then I have my, oh, I did not write my integral, I apologize. There we go. That works, right? P.S. Don't let them take away points from you. Write those d thetas. I'm not kidding. Don't let them take away points from you. Write the d thetas. Now can we integrate if we needed to? Don't need me to show you how to integrate with trig. Once we use the power reducing formula. Does it make sense? Why might someone want to go from 2 pi over 3 to just pi and then double it? It's half of it. Why would it be easier, though? Pi might be easier to plug in than 4 pi over 3. Easier fractions or something. Does that kind of make sense? So kind of like with even and odd, it might be a little bit easier, but you don't have to necessarily. It's up to you. Okay. What about this one? Uh-huh. Maybe. Noah's saying that it's just like a single argument, so it's not a 2 theta, 3 theta, 1/2 theta. So he's saying that the range would be just 0 to 2 pi. So what would you guys guess this is? Mm-hmm. Mm-hmm. Who is this guy, though? Just curious. Wouldn't I do pi over 6s, right? Why can't it ever be negative? Good. If I plug in 0, where else? At pi will be 0. At 2 pi will be 0 again if we kept going. Sine is 1 here, right? 1 squared is 1. Negative 1 squared is 1, right? Pi over 6 is 1/2 squared. Positive 1/2 squared. Negative 1/2 squared. Huh. I didn't do 11 pi over 6. So wait, what's going on here? So at 0, we're at 0, right? Pi over 6, we're at 1/4. We're not out very far. Then we're up here. Then we're back to 1/4. Then we're back here. Then we go 1/4. Then we go 1. Then we go. There we go. It's a little bit squished because this should have been a little bit further down. It would elongate it a little bit more. But yeah, it's like an infinity sign. It's like an infinity sign. How long does it take to complete? 2 pi. Are you guys going to be fine with 0 to 2 pi? Yeah. Could you have done 0 to pi and doubled it? Sure. But wait. How would you do this guy by hand? Okay, so 1/2, 1 minus. What's the dilemma with that still?
Would you have to do that?
How else would you do it?
Well, can't now sine to the fourth power, your u is sine. Oh, never mind.
Good idea, though. I wish. If there was a cosine, yeah. If there was a cosine, yeah. Now what? I can pull out a 1/4 to be a 1/8, right? Exactly. This was a hard idea when you guys were in pre-cal. But yeah, now you have a cosine squared, just whatever, go again. But here's the dilemma. When we go to go again,
it's -4x
now I'm going to have 1/2, 1 plus cosine. Why is it 4 theta? It's doubling whatever's inside. So if it's a 2 theta, double that. If it's a 3 theta, double that. Double whatever's inside for the power reducing. I wanted to make sure you guys saw that. Make sense? Those that don't normally answer, does that make sense? Go ahead, yeah.
Why is there, like at the top of the definition, why is it not?
Power reducing formula for sine squared has a minus instead. Cosine squared has a plus. Sine squared has a minus. Yeah. And so this one was minus, but then when we got down here, plus, but we had to double this guy instead of just doubling that guy. John?
I have a graph.
Yeah.
For like 3 pi over 2 and 7 pi over 6, if they were negative, they'd be overlapping, right?
It'd be overlapping. And why is it important if this was something different, like would sine of theta be a circle? It would, wouldn't it? Or an ellipse, at least. If it was something like sine of theta, let's think about him for a second. So there's no 1 plus or 1 plus 2 sine of theta or anything crazy like that. You guys would say 0 to 2 pi, right? But who is this guy? Yeah, but as you go around, right? Why is it important that we see that this overlaps? Why do you think I'm making a big deal about it? What's the period of sine of theta, guys? 0 to 2 pi. So wouldn't you just throw that in? 1/2 0 to 2 pi r squared? No big deal, right? But the dilemma is sine of 0 is 0, and then we have 0, then we have 0. That one's going to be 1, negative, nope, sorry, 1, negative 1. I left off 11 pi over 6 again, I'm sorry. I don't like doing more than I have to. I just ignore him. Then I would have 1/2, 1/2, negative 1/2. And technically, it is a circle. But you guys have figured out why I'm making a big deal about it, right? No? Zero, 1/2, 1, 1/2, 1. This is from 0 to pi. What happens right here? Negative 1/2. In your calculator, if you don't have that little circle showing, are you going to see that it goes around twice? You're just going to see it thinking when it finished. And you're like, why is it still thinking if it's finished? If you see a little circle, what are you going to see it do? Why is that important? If you looked at this and just did mental math on it, and I said the area within, what would most of you have done? But is that right? It's two times bigger than it needs to be. Because what's the period of this polar curve because it repeats? The period, you could say mathematically, it's going to go through a cycle of positives and negatives in 2 pi. That's true. But how long does it take to complete this one polar curve? You have to do 0 to pi. 0 to 2 pi would have been too big. Because in 2 pi, it goes around twice. So it would go and get all the area, and then it would go again and get more area. So is it enough just to look at the trig function and be like, yay, I know what's going on? No. Can it help? Yes. But remember yesterday when you guys were covering this, I should go ahead and finish. I apologize. Sine of theta squared d theta dot dot dot. When I gave you this page, remember I said there is no set definite way for me to tell you to find the bounds every time. It depends on the type of function, its behavior, its movement, its symmetry, its period. Brendan, put away your phone. It depends on all of those things. Okay? One more big idea. What if they want us to find area between two curves? We cannot think the old-fashioned way of top minus bottom, right minus left, because we're not doing that. We're not doing horizontal, vertical. We're doing, in a sense, diagonal. We're going out radii for polar. So we have to think differently. And some of you guys, the first thing you'll see as you're writing it is, wait, sometimes you subtract and sometimes you add? Don't worry, hang in there. Let me give you a second to get it down. And as you get it down, I'm going to pull up your Endeavor cards and see how we're doing. Who already has updated to number 32? Oh, we're fine. Okay, so this is going to be...
Yeah, it's 40. Were you about to write 4 hours?
Yeah. So this is 33, and then we have 34. Okay. The power reducing is 32. The power reducing is 32. The area within a polar is 33, and then area between is going to be 34. I did it again. Done. Okay. Areas between, found by subtracting versus adding. Now, this is not something that you're going to be memorizing. This is something you're going to be understanding, so it's not a big deal, and it doesn't seem super confusing. We need to understand why sometimes you're subtracting and sometimes you're adding. Now, one of the biggest things for us to get straight is that to find the bounds for the areas, I mean, we've always done intersections, right? Natural bounds between curves when we're trying to find the area or even volume of an area enclosed, either popping up in cross sections or being revolved. Like, we're used to finding natural bounds, right? Setting two functions equal to each other. Here's the struggle. If we're able to do it by hand, then the curves must be pretty stinking simple. Because if the curves get complicated, the by hand is going to be basically impossible. So by hand, they're going to be pretty simple. Obviously, we're going to have to know our unit circle. I mean, it's kind of silly that I'm writing it, but I am. By hand, they're going to be pretty simple in the map. Unit circle. You still should probably consider each of the different curves and what it looks like, and we'll try to show why that's important and why that's helpful. But by hand, it's pretty simple. Here's the struggle. By calculator, it's actually pretty complicated. Calculator is actually pretty complicated. Let me do an example. What if what if I was to give you these two? Let's not even write them in our notes right now. Let's go ahead and go to our calculators. Calculators, polar mode. Hopefully at least one person per group has a calculator. I want you guys to go ahead and put in 4 sine of theta. Then I want you to put in 2 cosine of 4 theta. How nice and easy would it be to solve for these intersections by hand?
I mean, by hand, not bad. Not so bad. By hand is hard. Because the interval, they change the bounds for the integration. For cosine. Anything by hand is hard.
No, I mean to find the intersections, set them equal to each other and solve. Wouldn't you have to think about like composite argument properties from pre-cal, like cosine of a plus b, and like cut it up? Or make this cosine of 2 times 2 theta, then use a double angle formula to break it up? You have to somehow break this 4 theta up, otherwise we're stuck from the very get-go and have nothing to do. So the by hand is going to be pretty complicated. Now, let's say we have the graph. Let me do zoom standard. Do these intersect? There's our, oh, yep, he has to go around a few times. All right, there he goes. Okay. Well,
That's kind of nice.
well, what's going on? Okay, I think we need to zoom in a little bit, right? Number one, let's zoom in.
Oh, maybe that's a little too much.
When you zoom in too much.
Oh, it goes around the circle twice?
Yeah, it's a sign of damages.
That does not look very.
It looks cool though.
Now, area between, number one is going to be pretty complicated, or semi-complicated. The area between is going to be a little rough, right? We can see that this is inside both, right? But couldn't there also be some inside both right here? Okay, no big deal. Like, this is easy, right? Intersections.
Why don't you zoom in a little more and see if there's anything?
Okay, here's the second dilemma, though. Can you guys put circles on the second guy, too, if you haven't yet? Put a circle on him. I just went past. Go to your window. Let's go ahead and make the theta step go by, why would I be making it go by 0.05s? What am I doing?
You're making it clearer.
Kind of.
Maybe I'm not.
And I'm also slowing it down. Más espacio, por favor, right? I'm slowing it down. We could go ahead and make our x, no, our y max, we can make that a little bit higher if we want. We can make it like a 3. Why am I doing that? Oh, wait a minute. I can't tell. Okay, pause. Can you also go to your mode, and can you actually change the sequential, which says, hey, graph in sequence. Graph the first one entirely, then graph the second one entirely. Go to simultaneous. Do they cross? Ooh, yeah. Where else do they cross? No. Okay. So do they cross? Do they have intersections? Yes. Ooh, but do you see the struggle with the intersections? There was an intersection and an intersection, but does that hold in all the leaves that I need? Okay, that's going to be a little bit of a struggle. We saw 2 intersections, but we still can't solve for them in polar, and I just said by hand it would be really ridiculous to do. What are we going to do in our calculator in order to find these intersections? Go to the mode that says I can do that.
Wait, but how am I supposed to?
Put in the curves that we have, which is sine of x, right? No, it was 4 sine of x? 4 sine of x. I know.
2 cosine 4x.
Thank you. Why am I going to make sure that my x min, well, x min doesn't really matter, but my x max is 6.28?
Because that's too.
When you graph in function mode, aren't the x's now thetas and the y's now r's? Because r equals y equals function of thetas, function of x's. So I wanted my thetas, my 0 to 2 pi, to be shown, right? Now I can go ahead and graph and say, all right, where are you? You see it? You see it? What can I do in this mode? I can find them because I can do second calc and I can do intersect. But when I do intersect, I have to remember that my x is going to be my theta and my y is going to be my r. Does this look like the curve I just had? No. But can I find the intersections that I need? Yes. There's my theta, there's my r if I needed it. Okay, so what I was saying by complicated, couple hints. First of all, I would say you should go to simultaneous. I would say you should do the circle with the line. And I would say that you can go to function mode in order to do the intersect feature. But you need to be careful with your window. Simultaneous mode, the little circle with the line, and function mode. Here's the struggle, guys. Do you know how I was asking you, do they intersect?
Yes.
It is possible for curves to look like they intersect, and their paths do, but the objects moving on the path would not. Does that make sense? Two roads that cross, but just because they cross doesn't mean that the cars will crash, right? Because what if the car goes through the intersection at different times? They're not going to crash. It's fine. But why is that a dilemma when we're dealing with this? It wouldn't be an intersection point in function mode if they don't pass at the same time. So that's why I'm saying also put the circle there, because if the circle's there, we'll see if they actually crash. Hence, we can put it in function mode and find it, because if they don't crash, we're going to have to think of some other way to get that intersection point. I've only seen that on an APFRQ once, but it was fairly recently. Okay. I want you guys to think through this, yeah? Find the area of the region that lies inside the circle r equals 1. You guys see him, right? Where's r equals 1 in the picture? This one, right? Just a circle. R equals 1. Go up 1, back 1, down 1. Okay. And then what's my other shape? Cardioid. Now hold on. When it says inside the circle and outside the cardioid, what's it talking about?
The other side.
Right part of the circle.
That one. That one.
Yeah, right there.
Doesn't that seem kind of easy?
Kinda. But no.
But what's the struggle?
It's not.
If I zoom in, it's going to be a little rough because I think this is all one snapshot. Oh, no, it's not. Okay, hold on. That didn't work. If I was to just go to the circle, do you see where I would have some issues? Why do I have to consider the cardioid at all, right? Isn't it just going to the circle, going to the circle, going to the circle, going to the circle? Do you see where I'd start to have problems? There's cardioid in the way. I can't just go to the circle because there's cardioid in the way. So I'm not just going to go to the circle. Now, hold on. Do I want any of that? No. You guys know how circle graphs and polar, right? And then we'd have to come back here, and then we'd go, once again, cardioid in the way, cardioid in the way, cardioid in the way, cardioid in the way. What do I do? I need to subtract the circle's radius, the outer, minus the cardioid's radius. Because if I can subtract the cardioid's radius for the same interval, hopefully they're happening at the same time with the same bounds. But if I can subtract the circle's area minus the cardioid's area, will I get the in-between? Yes. And then I really just need to focus on, like Noah said, this part of it, and then I can double it, right? I don't have to go and then wait and then come back and split up my bounds. So let's think about this. How are we going to figure out when they intersect, if they intersect? That's kind of an important point, right? Okay, so intersection, let's see if it's easy by hand. Is it easy by hand? Looks easy by hand, right? Because I can subtract 1, 0 equals negative cosine, hence cosine equals 0, which is going to occur. Not x, theta. Okay, what's the good news? Hold on. What's the good news if I see only 2 intersections and I solve for 2 intersections? What's the good news? If these are the only places where the roads pass, and if I know that they have to collide, those are my 2 intersections. There's no the circles are passing like ships in the night and not realizing, not actually intersecting. Because on polar curves, there are false intersections where the paths cross and the cars don't. But since I solved for it and the math said yes, okay, fine, they're intersections, no big deal. Why am I going to go ahead and then go to the page before and say, okay, this is going to be one of those subtracting examples. Why do I know it's subtracting? I have to take the outer and I have to take away the inner, right? Okay, just natural. It's subtracting, no big deal. So therefore, I'm going to go ahead and what's the formula that we're using? A equals 1/2. Oh, just the formula, right? 1/2 r squared minus 1/2 r squared, outer minus inner. Kind of like whole minus hollow, sort of, a little bit different. I could technically take out the whole 1/2 if you want, that's okay, and make one big integral in this case because they're going to have the exact same bounds. The circle, if you guys were to actually graph it, goes from 0 to pi over 2, and the cardioid goes from 0 to pi over 2. Since they're moving in a sense like in tandem along their curves, it's okay. There are times sometimes when this one's 0 to pi over 2 and that one might be a different boundage, which is why they have them separate in the formula. But for right now, since they're traveling the same way, 0 to pi over 2, I can just subtract the outer, which is which one? Squared, minus, this kind of reminds you of washers, yeah? I'm putting it all in one integral because I can, because of the bounds, since they match up. If I was to put this in my calculator, I would see the two little circles moving together and being like, yay, woohoo, and then just subtract and you're good. The problem is, what if I have this guy going here and this guy going here, and it's like, yay, woohoo, and then it comes back later. I couldn't subtract this over here. I'd have to wait until it comes to where it needs to be. Anyway, so all sorts of interesting things that can happen. What would you do to finish? Solve. Yes, because we need to go ahead. Sorry, I was just doing 1/2 of it. Oh, I came back, right? Because that would just get us the top region. Times 2 would get us our entire answer. Thanks, Lucy. What about this guy? Who's who?
Bigger circle, small circle.
Half circle, E. That's r equals 2. It's a circle. And can't you guys also see the cusp?
Yeah.
Okay. You guys are reading what they're asking, right? What area?
The region between the curves.
Inside both of them.
Oh, so it's just not that little red part. It's just that right there.
So I want all of this, right? Wait, why do I need to stop right there? If I keep going to red, it's not going to work. So what am I going to do? I'm going to add, starting here. And why am I going to stop right here? Psh, double it. I'm going to do my circle. Then I need to switch and go to my cardioids. I'm going to do this one plus that one. Are the bounds going to be the same? I doubt it. Right? Because the cardioid's doing this for this whole time. I need to wait until the intersection point. So let's call this intersection point A because we're cool like that and we can do that in calc. How would you find that intersection point? Maybe you said equal? It would work. It's not too bad. But then you would go ahead and do 1/2 times 0 to A of, 0 to A, who am I going to find the area of? That's the circle. Plus 1/2, A to pi. Probably pi, right? Oh, this is my A, probably. Right? Of, who's going to be in this one? Yeah. I'm going to plug it in as you guys go ahead and pack up and go. Homework, due tomorrow, do the best you can, come with questions. That's going to be my circle.
Yeah, Kyle, let's go.
And that's going to be my, Gabby, go ahead, kid.
Oh wait, never mind. I read the question and answered my question. Because I was wondering why you